Okay, in this video we're going to talk about the basic ideas behind systems. We'll first talk about some very simple systems that the operations they perform in the input signal to produce an output are quite simple and straightforward. We're then going to talk about how you can hook systems together to make more complicated input-output relationships, the relationship between the input and the output. And then finally we're going to talk about linear systems and then time invariant systems. And the ones that are both linear and time invariant are going to be extremely important to us, as we're going to see. All right, so let's talk about some simple systems, ones that are pretty easy to understand. And the first one is quite simple. It's called a gain. And what this system does is the output is equal to the input times a gain, a number g, a scalar. So I think that's pretty easy to understand. It just takes the input, multiplies it times a number, and that's its output. So you can use the unit step as a example input to see how this works. So the input here, as I've drawn it, is a unit step, and then the output is the same unit step, except it's now got an amplitude of g instead of 1, whatever that is. This special case that I've indicated here of an amplifier has to do with the fact that if g is bigger than 1, the terminology is that it is an amplifier. It makes things bigger. It amplifies. There are cases in which g is less than 1, in which case it serves as an attenuator. It makes things smaller. And finally, a somewhat confusing terminology, if g is negative, it's called an inverter. So it does not mean take the reciprocal. So if we use our unit step input, for example, here, so we bring in a unit step, and we look at what the output's going to be. If g was negative, the output would be like that. So it doesn't mean take the reciprocal, it means change the sign. I don't know where the terminology inverter came from, but that's what it is. Okay, let's talk about some more systems. And this one we've seen already. The time delay. The output is equal to the input a little bit later. It's been delayed. And again, using the unit step as our example, you delay, the output is also a unit step, but it's now delayed. We've seen this, like I said already, in talking about signals. Pretty easy to understand what it does. Turns out it's a bit more complicated to build. So delay boxes turn out to not be easy. We do want to point out that they do occur naturally. Light, in fact, all electrical signals travel at a finite speed. They don't travel from one place to another instantly. So if something happens at the sun, a change in the brightness of the sun, it won't reach the Earth for about 8.5 minutes. So that's a delay. So that's a physical delay. Just running an electrical signal through a long piece of wire introduces a delay. So in some cases it's pretty easy. It's very hard to have a controllable delay, though. That could be a bit more complicated. So, like I said last time, if you have tau greater than 0, that's called a time delay. If tau is negative, it's a time advance. It occurs earlier in time. Turns out such systems are pretty hard to build because, again, using our unit step as an example, if tau were negative, the output would come out before the change in the input occurred. So if this is, for example, at -1, this output at time -1 is going to have to occur before it occurs at the input. So somehow the system would have to know the future value, the future behavior of the input signal. You know, that's a little weird. And so time advances are great mathematical things, but building them is more than just a little complicated. I have another example that's along similar lines, something that's easy to write but hard to build, and that's called time reversal. So here, using our unit step input, you put in the unit step, and it comes out delayed. Not delayed, I'm sorry. Mistake, it comes out time reversed. So notice that again, the value at, let's say, time -1 is going to be the value of the input at time 1. The system would have to know what was going to happen 2 seconds ahead, in that case, to produce an output. Well, it gets even worse. What happened at time 10 would have to come out at the output at time -10, which means it would have to be able to predict way ahead in the future. In fact, predict the entire waveform into the infinite future and then put it out at the infinite past. So time reverse systems are very weird, very hard to build. However, they have a very simple mathematical description. Not all simple systems can be built. Well, let's talk about some systems that are maybe not so simple, but easy to understand. And that's the derivative system. So what this system does is simply take the input and evaluate its derivative, and that produces the output. So easy to understand, and actually derivative systems are actually easy to build. We can also talk about systems that integrate, and I want to point out something about this. Again, these are easy to build, but there's a convention in this course that's important. And that is, there are no such things as indefinite intervals in this course. Every integral is a definite integral. And most of our integrals will start at -infinity and go up to time t. I tend to use Greek letters for variables of integration. It's just a convention I have to make it clear that it is a variable of integration. This will come up pretty frequently. So the output y is equal to the integral over all previous time of the input x. And like I said, there is no trouble building this system. Okay, those are our simple systems. Let's put them together. So let's talk about some simple structures. Perhaps the simplest is called the cascade structure. And essentially, all it has is one system after another. We've already seen this in the fundamental model of communication. It is a cascade of several systems, in fact 5 of them. So the input to the entire chain is x, goes through S1, produces W, and then W in turn produces Y. So we can think about this as one system which is constructed as a cascade of 2 simpler systems. In fact, that's exactly what cascade structures are for. For example, suppose you wanted a system that delayed and inverted. Well, I could do that by building an inverter, let's say here, and then passing that, the output of the inverter, into a delay. And then the overall relationship between x and y would be an inverted delay. So that's the way you get something a bit more complicated from simpler systems. Another way you can hook systems together to do interesting things is what's called a parallel connection, and I think it's pretty easy to see why. They're in parallel. You have 2 systems here that run parallel to each other. There are a couple of conventions here we need to talk about. I want you to notice here that I have x coming in and it gets split. At least that's what the diagram is seen to indicate. In system theory, the convention is that when such a split occurs, it doesn't mean split the signal in 2 or anything. What it means is the same signal is applied to both systems after the split. So it's just a convention. That's why I labeled this very carefully x of t. When we get to talking about this in